Okay, I think that's working. Hi everyone, again, my name is Jennifer. Thank you so much for the introduction. Today, my presentation will be on my research on input-output specifications of grid-forming functions and data-driven verification methods. So grid-forming technology has become a really big topic recently, and we are all trying to understand what is grid-forming control. And while many different definitions and implementations of grid-forming control exist, there is currently no one accepted definition. And one common approach used to clarify what we each mean when we use the term grid forming is to detail the internal control structure and compare how it differs from existing grid following technology. This usually calls for closely looking at various block diagrams and seeing how they fit under their assigned labels. Unfortunately, this method does not fully capture all existing control schemes, and it's unclear how it can be applied to emerging control technologies. And so in my work, I explore a different perspective on how to characterize a device. So first we begin with this idea of performance and stability as a spectrum. And performance and stability are two important aspects when considering the deployment of any device. And in this illustrative example, we have grid following and grid forming devices spanning these regions on the spectrum. And we have shown here that some grid forming devices perform better than some grid following devices and vice versa. And because of this wide-ranging possibilities of outcomes, it may become necessary to impose requirements on the devices to ensure that we get what we expect or what we want from the converters. So we can start off by defining some basic specifications that most converters can meet. And then we can also develop some advanced specifications that only grid forming converters can meet. And whatever the level of the specification, they all help ensure interoperability between the converters as well as with legacy devices. So moreover, the main idea here is that we distinguish devices using system and device level requirements. So based on which specifications a device can meet. How do we do this? So one useful tool here is input-output modeling, where the objective is to characterize the dynamic response of a converter interface generation, or CIG, at the point of interconnection using only input-output data. And a big advantage here is that this is a technology and controls agnostic approach, meaning that it is not required that we know the internal control structure or embedded hardware. Instead, we focus on this idea that this idea here is that the converter is connected to a network or grid, and we use measurable and accessible data collected at this interconnection bus here to characterize the converter's behavior. And so these measurements can be used also to define different input-output pairs that correspond to different functions of interest. With that said, let's discuss how input-output modeling can give us a better insight on interoperability. And in this work, we specifically mean interoperability of frequency dynamics, or frequency stability under interconnection, which restricts the interactions between devices on the same network. And to better assess interoperability, we begin by abstractly capturing the network using some key parameters or key properties such as XR ratios, impedances, nominal frequency, and bus voltages. And using these properties, we are able to develop a decentralized stability condition that translates system-level needs into device-level requirements or specifications. We can then test whether each device satisfies the stability condition individually. And this is how, using just input output data, and this is how we can certify interoperability between devices. So to develop these specifications, we model the converter interface generation as such, where we have the inputs and outputs, again, specifically related to what we can measure at the inverter or converter bus. And so this matrix here captures the CIG bus dynamics. And another model we used is this linearized line model that captures the transmission line dynamics, where we have power flow here, active and reactive power, and we have the phase angle differences and voltage difference here. And since we're interested in frequency dynamics, we focus on this first element, which captures the relationship between active power and phase angle difference. And you may recognize this scalar term. You may recognize this scalar term, which alone describes decoupled power flow. We extend this relationship to include this frequency-dependent component here that accounts for the circuit dynamics of the network components. And so this model can capture line dynamics of faster timescales instead of just a steady state dynamics. So using these models, we were able to develop an interoperability specification in which interoperability between converters is guaranteed if the decentralized stability condition is satisfied for each device. And this specification has a graphical interpretation that makes its application more convenient. For that, we look at this transfer function here, which has two components. The first component here captures the network or system and device properties. And this second component here, which you may recognize from the converter model, is the converter bus dynamics, specifically this relationship between active power and frequency. And so let's look at, So using this transfer function, we look at the Nyquist curve of this transfer function, and if the Nyquist curve is contained within a half plane crossing -1 and 0 with the angle alpha, then the converter passes the decentralized stability condition. And so if all of the curves are of different devices are contained within one half plane, then we can guarantee stability of those devices. So looking at an example here, this Nyquist plot comes from reduced order models of grid forming and grid following converters. So that's how I get this component here in the transfer function needed to plot this Nyquist plot. And so as you can see here, these two curves exist within this half plane here that crosses -1, 0 and has this angle alpha between 0 and ½ pi. And so with the conditions or the network and device properties used to obtain these curves, we are able to guarantee the interoperability between these two devices. And if the network and device parameters change, or these devices are implemented in another network, for example, then the Nyquist curves will change. And in that case, alpha can be adjusted to define another half plane that captures the new Nyquist curves and ensure the stability margin between the Nyquist curve and the half plane. So stability does not imply performance. So we sought to develop some separate performance specifications, and we based these specifications on the concept of disturbance response, or the converter's ability to suppress disturbances at the interconnection bus. And in this case, the inputs come from another source here. So in this 2-bus system, we have one source here and the device under test, say a converter. And we are looking specifically at how disturbances coming from another source affect the response of the converter at this bus. And we can develop, using this framework, we can develop some performance specifications related to different functions, including oscillation damping, synchronization, and load sharing. So here's one example of a performance specification that we developed. It is called Oscillation Damping and describes a device's ability to reduce high frequency fluctuations at the interconnection bus. Since we are interested in frequency stability, we look at how frequency at the converter bus responds to perturbations or disturbances coming from another source. So this is the transfer function that captures that relationship here. So this transfer function, actually we found that it directly translates to bounds on the Bode magnitude plot with the upper limit shown here. So after arriving at this transfer function, we found that there is an upper limit on the magnitude of this transfer function. So let's look at some more examples. Again, these examples come from using reduced order models. Again, we're looking at this frequency to frequency transfer function. And we see that in the grid forming with droop case, that in the low frequency region, when the perturbation frequency is low, we do see synchronization. So neither amplification nor attenuation. In the high frequency region, so when the oscillations become faster, there is a high frequency roll-off, meaning that the converter is able to provide damping and reduce the oscillations from coming to the inverter or converter bus. In the case of the grid following converter, we find that, again, in the low frequency region, there is this synchronization. However, there is no high frequency roll-off. And actually, there is a limited range of attenuation compared to that of the grid forming case. And so it is, and the overall shape here of the curve does not change, we found does not change with different tuning of the this specific implementation of grid following. And so it is that from this result that we propose that the synchronous reference frame phase lock loop grid following control case cannot meet this oscillation damping specification. So moving on from this analytical study to a numerical study, I will now present a method we developed for validating these proposed interoperability and performance specifications and show how to apply it using input-output data obtained from detailed EMT simulations. So we begin with designing the probing signal. Here in this 2-bus system, this is the device under test, and this is another source. And the voltage waveform of that source is defined as follows with a voltage magnitude and frequency. The disturbance is designed as a oscillation around the nominal values of voltage magnitude and frequency, where these parameters, the amplitude and frequency of the oscillations, are values that we can choose. And for each perturbation frequency, so omega p, 2 experiments are performed to separately perturb the 2 parameters, voltage magnitude and frequency. And this is so that we can isolate the effect of each parameter on the other signals. So the second step here is to obtain the output data, which pertains to the converter bus, again here. And so we measure some signals, including the three-phase voltage and the power injections, and we perform a Fourier transform to obtain the amplitude and phase shifts of the resulting oscillations in the output signals that correspond to the perturbation frequency applied. And after obtaining all of the input-output data from the simulations, we recover the transfer function of the CIG bus dynamics shown here by solving this equation. So here's one result from our numerical study. This Nyquist plot was obtained using the input-output data from the simulations following the methodology I just outlined. And the Nyquist curves here, if you can recall, actually resemble that or those from the analytical predictions shown earlier. And this confirms that it is possible to recover the transfer functions needed to certify interoperability using just input-output data. So this is a really interesting result. And in this specific example, both of these converters here, one grid forming and one grid following, we're able to certify interoperability between them because we are able to define this half plane here. So thus we can guarantee interoperability without knowing what's inside the devices. So now we'll look at some numerical Bode magnitude plots needed to certify the performance specifications. And for oscillation damping, we focus on the frequency to frequency transfer function. For the grid forming case, we found that the tuning of the cascaded inner control loop significantly impacts the oscillation damping performance, in that if not tuned properly, it can add resonance and amplify disturbances here. And however, this cascaded inner loop control does provide better control of the bus dynamics. So there is this trade-off between the performance here, but then also control of the bus dynamics. So in the case of the grid following control, we found that coupling strength can play an important role in the performance. So a stiffer connection between the converter and another source can reduce the converter's disturbance attenuation, or ability to attenuate the incoming disturbances. However, this result can be interpreted as better synchronization between the converter and the second source. And so here, the performance specifications are all about understanding what to expect from a device and deciding whether that fits what you're looking for. So in conclusion, we investigated, in this work, we investigated external characterization of CIG's converter interface generation to avoid digging inside devices. We use input-output modeling to develop interoperability and performance specifications to characterize these devices. And we also proposed a data-driven method to validate that the devices meet said specifications. We provided some results from numerical studies showing that we are able to recover the transfer functions needed to help certify these specifications from just input-output data. And we also investigated how the converter dynamics are impacted by different network and device properties. In future work, we hope to also look at how to develop specifications using Bode phase plots, such as imposing specification or requirements on delays. And we also hope to look at networks with heterogeneous RX ratios. So this is because one of the assumptions we made to formulate our decentralized stability condition is that all of the connections have the same XR ratios, but this can be a conservative assumption. And finally, this would be really exciting to implement this work in a hardware experiment to further understand the application in the real world of input-output modeling. So thank you so much. That's it for today.
Thank you very much, Jennifer. So maybe let's go to the second speaker and then we have do the Q&A together. Would that work for you, TG?
Yeah, that works for me.
Okay. Great. Thank you.
All right, I think that you all should be able to see my screen. Let me just move these controls really quick. All right, so thank you for the introduction. Really quickly for anyone who missed it, my name is T.G. Roberts and I'm a PhD student at the University of Illinois, Urbana-Champaign. And I work under Alejandro Dominguez Garcia in the Department of Electrical and Computer Engineering. So the presentation that I have for you all today is on secondary frequency and voltage control and microgrids with dVOC-based inverters. And at the very end, I will also include some of the controller hardware in the loop that we are working on in our lab at the U of I. So, okay, cool. Some background in order to motivate our research is that as inverter-based resources begin to replace synchronous generators, we face a real lack of inertia in our systems that normally keeps voltage and frequency stable, especially in microgrids. So with grid-forming inverters, we're able to develop control algorithms that help keep this frequency and voltage stable without the need of inertia from synchronous generation. So in a general power system, we have normally a three-tiered control scheme where the primary control stabilizes frequency and voltage after a disturbance. So say a load change happens, our frequency might settle to a new stable operating point, but it won't be at 60 hertz. Maybe it'll be 60.1 hertz or some other value, which is where secondary control comes in. So with secondary control, we're able to return frequency or voltage to nominal after a disturbance, as well as regulate tie line flow. That's not something that I'm going to talk about in terms of microgrids. And then the third tier is tertiary control, which comes in the form of economic dispatch, which is also something that I'm not going to really get into now, but I will mention it briefly later. So kind of as a background literature review, why have we chosen to look at dispatchable virtual oscillator controlled grid forming inverters for the primary control? Droop is normally the one that is looked at for the primary control level, even with diverse types of secondary control. So in the literature, people have done proportional integral derivative secondary frequency control, as well as proportional derivative secondary control, among many other types of secondary control. But we really wanted to look at applying these types of secondary control to the dVOC-based primary. This is because dVOC has shown to better stabilize frequency and voltage for arbitrary initial conditions and have better dynamic performance than Droop. So these dVOC equations are based on the Hopf oscillator circuit, which is a type of weakly nonlinear control. And I will get into the actual equations in a second, but this is just some motivation for why we chose to do this. So the overall goal of our system is to use dVOC-based primary control, as well as secondary frequency and voltage control to regulate voltage and frequency in a system to nominal after load disturbances occur. So now we need to motivate the network model a bit. These equations should be recognizable as the power flow equations in our system, albeit in the discrete form. So essentially we have P as our active power injected at bus I into the network, and the same thing for Q, where voltage at bus I is VI, voltage at bus J is VJ, and then we have the phase angles at the buses as theta I and theta J, and then XIJ denotes the reactance between buses I and J, and BII denotes the entry of the susceptance matrix. So there are some microgrid assumptions that we have to make that are kind of reflected in these equations. So these are the assumptions that we're making in terms of our microgrid. we are saying that it is balanced and operating in sinusoidal regime, that there is one transmission line connecting each pair of buses that is short and lossless. So as of this paper that was presented, we do not have resistance included in the model. And each bus has a generating or a load type inverter-based resource. So this is important in the sense that if we have a load in the system, it's interfaced through a grid forming inverter. This generally has made the math a bit easier, which is why we chose to do this in the first place. And there's also small reactance of the voltage source compared to the network transmission lines, which means that we're neglecting the impedance between the generation source and the bus. So there's no E's in terms of voltage or deltas in terms of the phase angle. E and V are equivalent and delta and theta are equivalent. So now let's get into the actual primary control model for dVOC. This is the frequency control, which is the discretized version, and it might look quite similar to the Droop equation. So for example, if we move this theta to the left-hand side and then divide by T, on the left-hand side, we'll get a derivative in terms of the phase angle. So then we have this as our Droop constant, and then we have P circle minus P. So notably, a difference from Droop is that this constant is not actually constant, is in terms of voltage, and it's also nonlinear, so it's squared. And then this AI term is a parameter that comes from the derivation from the Andronov-Hopf oscillator circuit. Something that I mentioned before in terms of each bus in the system either having a generation source interfaced with a grid forming inverter or a demand means that this P circle will either be PD for all of the loads or PR for the resource. So this is a reference value. Something similar occurs for the voltage control for the dVOC-based primary control. So if we ignore this term in the middle really quickly, we have VI K plus 1. So if we move VI to the left-hand side and then divide by time, we get a similar dynamic equation here with our Droop constant, which is also not constant, but it's linear in this case. So it's essentially 1 over V with our constant AI, again, coming from the Andronov-Hopf oscillator circuit. And then the same thing happens with our Q circle. So if it's a load bus that's interfaced through a grid forming inverter, it would be QID for the demand. Or if it's a generation bus, then it would be QR for the resource. This extra term here comes in due to the nonlinear nature of the oscillator circuit. So we just have an extra term that is derived from there. But if we ignore this and assume that our VI is close to VI circle, then it kind of collapses down a bit in order to have a similar structure as frequency. So now let's get into the actual control that we have developed. So this is the closed loop secondary frequency and voltage control for our system. So here we have the actual controller, which is an integral controller, again in discrete time, where the control variable Y is updated with the weighted average frequency error, which is essentially the sum of all of the demand in the system and all of the resources, the references. So if this is 0, then we have no frequency mismatch in the system, which means that we have no more or further control effort. But if there is a mismatch in this, then our average frequency error will be non-zero, which means we have an updated Y value, which then gets plugged into this part of the equation. And we're updating our reference, which was the input to the primary controller in the last few slides. And then our alpha and beta are our controller gains, and PI star is the active power reference that comes from tertiary control. One notable thing here for our secondary frequency control is that Y is not in terms of I, and this happens because we have one controller for our entire system, because frequency is not a local measurement. So this is a centralized controller. This is different for voltage because voltage is a local variable. So we have a different Z control variable for each bus. So essentially the structure for our secondary voltage controller is very similar to that of frequency, where we have our difference in what we want voltage to be V star versus what it actually is V. That will be our voltage difference, which will help us update our Zi at the k+1 time step. If that is updated, it gets plugged into this reference command equation. And again, Qi star is the reactive power reference command from tertiary control at bus I. So this QR reference command will go into the primary control equation for voltage. So this has been the development for the two secondary control equations. So now let's look at some simulation results. So for this paper, we had a test system as a 3-bus network where buses 2 and 3 were the generating grid forming inverters. So they were sending power to bus 1. So this bus 1 is a load bus. So power is essentially flowing this way and this way. So this simulation result shows the simulation without secondary control added. So we see the active power load change here over 200 seconds. And then at each time step, primary control stabilizes our frequency. So this is frequency mismatch. We want it to be at 0. So it's frequency minus 60 hertz or yeah. So we want it to be at 0, but it is slightly off from 0 and deviating away, but it is stable. So I will show in a minute what happens when we implement our secondary frequency controller. But first, let's look at what happens to the reactive power load changes. So here we have our reactive power load profile. And then this is the voltage load profile without secondary control. So we can see that it's not quite centered around 1 per unit for voltage, but our secondary controller will remedy this. So this is what happens when we implement our frequency and voltage secondary control. We can see that not only is frequency stabilized, but it is brought back to nominal. And the same thing with the voltages at the generator buses. Now, the voltage for V1 is not brought back to 1 per unit of nominal because this is a load bus. So we don't really have control over what the voltage is at this bus. So as a recap, what we have done so far is we have developed a model for a fully inverter-based microgrid with dVOC-based primary control, as well as secondary frequency and voltage control. And the simulation results showed that our control scheme is able to regulate frequency and voltage back to nominal after multiple disturbances. So some future work, including the hardware in the loop implementation. So what we want to do in the future is include a voltage behind the reactance model. So no longer have V and E equal to each other and delta and theta equal to each other. We also want to make our system a bit more realistic by including resistive lines because microgrids generally have higher RX ratios. And we also want to include multiple resources on each bus, including maybe a load or multiple grid forming inverters on each bus. So now I'm going to talk about a bit about the controller hardware in the loop lab that we have set up at the U of I. So what exactly is hardware in the loop? When we begin simulations, we normally begin a test with MATLAB or Python in order to test our controllers. The next step in validating models is to test with real-time simulation hardware that gives us the ability to run more high-fidelity models and test our controller on them. So the power system itself will run on the real-time simulator while we can deploy our controller on the control hardware. So why do we want to use something like C-Hill? It gives us the ability to run more high fidelity simulations because this hardware is much more powerful than MATLAB. So normally if we're running something in MATLAB, it could take hours to run a 10-minute simulation. Whereas something like this, it will run 1 second in real time as 1 second in simulation time, which is extremely powerful for us to use. It also gives us the ability to include physical hardware in the system, which is something that we will possibly be deploying in the future. So there's another type of hardware in the loop called P-Hill, which is power hardware in the loop. So there's the possibility of including future actual generation in the system and not only controller hardware. But as we are testing our controllers, that's why we're using the C-Hill. It's also more efficient, so we have less risk and ability to rapidly prototype. So if we want to try out some new controller, we have the capability of doing that without risking actual generation sources, or for lack of a better word, blowing up a generator. So it's just more efficient to be able to test on some controller hardware in the loop. So these are some of the devices that we have in our actual lab. So this is the Typhon Hill 604. There's 5 of them. And then the bottom here is where we could actually connect a real inverter, but this is not currently connected. So the real-time simulations for the power system will run on these, where again, our controller hardware is running on the Typhon Hill 404. This is more of a custom hardware that they've built for us. So I'm calling it the HIL 404, but it's slightly modified from the base model of the 404. Part of the reason that we wanted to remove the controller from just running on one of these 604s is we wanted to be in a more easily deployable system where we could pick this up and go plug it into an actual system instead of having to take this whole rack on the left. It also allows us to free up more space on the 604s in order to run more high fidelity models. So here's a sample system of some of the types of controllers that we can test on a system like this. So one of the things that we have currently deployed is the synchronizer, which is what I will be showing a demo on in a minute. Say that we have this system over here on the right already running. So we have this grid forming inverter feeding this PQ load, and we want to be able to connect this grid forming inverter on the left to this system. We need to be able to synchronize the terminal voltage, the phase, and the frequency exactly in order to connect them, which is what our synchronizer does. So once these two things are synchronized, they will connect. And then we will be able to run something like our secondary control as another layer on top of that. And everything in orange would be run on the target hardware, which is the HIL 404s, and everything in black on this slide would be run on the 604s. So far in our hardware setup that we have deployed, we have only deployed the synchronizer, which is what I'm going to show a demo of in the next few slides. So this is a very simple test system that is showing kind of proof of concept of the synchronization algorithm that we've developed for a Drupe-based grid forming inverter connecting to an infinite bus. So what you will see in the next slide is a video of the Typhon Hill SCADA system where we can monitor the voltage and power exchange between these two components. The grid forming inverter, power stage, the filter, the inner current and outer voltage loops, as well as Drupe control are all emulated in the 604. So essentially everything you see here except the synchronizer is implemented in the Hill 604s, and the synchronizer itself is implemented in the target hardware on the 404s. So the way that the 604s and the 404 talks to each other is through a wired communication protocol called Modbus. Okay, so the experiment will be as follows. Initially, when I press play, you will see that the Modbus state here begins at 0, which means that there's no communication between the 404s and the 604s. Shortly after, you will see the Modbus state change to 1, which means that communication between the two is established. So, okay, upon issuing a manual command, the synchronizer will attempt to synchronize the grid forming inverter to the infinite bus. So here Modbus state turns to 1. And then when we click connect in just a second, we will see that the voltage for the grid forming inverter and the infinite bus will try to synchronize, which it just has. This is the injection of the active power from the grid forming inverter, which in this case is slightly offset from our reference value P star. And that's because in order for synchronization to occur, there's a small mismatch in inverter frequency. We have to basically tell the inverter to spin a little faster in order to reach the target frequency. So if we then remove that offset with this button, we should see the reference drop to 0 over here. And then we are able to then put a target set point here. So we're doing 1E6 watts, and we should see our power injection jump up to that, which it does. So we have perfect tracking in this case of active power that our target grid forming inverter is sending into the system. So we can once again change the set point here and see our power injection drop. Okay, so this demonstration illustrates that we have a working synchronization algorithm on our target control hardware. Our next steps are to now include secondary control algorithms in the same system and to also include a larger test system. So with that, I will end my presentation. Thank you for listening.
Okay, thank you so much for the presentations from both of you.